Okay, so I'm going to do an example with Greens Theorem. Just let me remind you what I was saying last time, which again, this is all that you really need to know. You don't need to understand the explanation for how we found Greens Theorem. But the idea is, imagine that you have a closed curve, which is this pink curve that you see here. The curve is being traveled by an observer in such a way that as you move along this curve, the region enclosed by the curve is to your left. Okay, so another way to say that would be in this example that is like counterclockwise. Although in general you have to be a bit more careful about that. But so the statement of Greens theorem is that the line integral, right? If you want to compute the work, you will need to do an integral of this form, right? And what Greens theorem says is that actually you can avoid doing this ordinary integral that we have been doing before, and instead you can just compute a double integral of something. You have to integrate some function on this region, and the function that you integrate is this difference of partial derivatives. So F1 and F2 refer to the two components of the force field that you have. So there's a vector field F, and what the statement of the theorem says is that instead of doing this integral, you can do instead this other integral. And again, for now, this may look just like a nice observation, but this will hold the key to understanding when a vector field is conservative. And I'll explain that in a couple of videos once we start discussing Stokes' theorem. But so let's do an example for of this to illustrate Greens theorem. So let's try to use it to find the work done by a vector field F. So I'm giving you some vector field, which is x minus y, I, so that's the first component of the vector field, and x in j, so this is F1 and F2. And we want to compute the work along the curve, which is just a unit circle. So you want to compute the work along the unit circle. And so again, you could do this instead, do the line integral or do the ordinary integral, which is how we did compute work at the beginning of these videos when we started talking about this topic. But what I'm trying to say now is that it is no longer necessary to compute the work in that way. Rather, you can just apply Greens theorem. And so according to Greens theorem, what you need to do is compute a double integral, which is the following. So you need to do a double integral of what? A double integral over R. R is in this case the unit disk, right? And of what? Well, you have to put inside here the partial derivative of F2 with respect to x minus the partial derivative of F1 with respect to y, dA, I don't want to erase the statement because we'll use it also for the next video. So the partial derivative of F2 with respect to x is just is 1 minus the partial derivative of F1 with respect to y, which is minus 1 times the A. And again, this integral is being done over the unit disk. And so this is, well, this gives you 2, so you get 2 times the integral of the A over the unit disk. This is fairly straightforward because you could just say, well, this is the area, and the area of the circle is pi r squared, so you already know the answer. But you can also just use polar coordinates, and so this is like the integral from 0 to 2 pi, from 0 to 1 of r dr d theta. Right? Remember that the A in polar coordinates is r dr d theta, and this again will give you eventually will give you just pi, so you get 2 pi. So in other words, the work, so what we found is the work here is 2 pi. Here's a nice observation about this calculation. If I had asked you, oh, is this vector field conservative or not? Well, you would have to say that it is not conservative, because if it were conservative, then the line integrals along loops are always 0. Along closed loops are always 0, but we already found that the line integral had to be 2 pi. And on the PDF, you can check the other way to compute this just using the ordinary integral in terms of the velocity, and you can see that they indeed give you the same answer. Well, in this case, it's fairly straightforward, so if you want, we can do it. It would have to be just so that you see that you get 2 pi as well. It would be the integral from 0 to 2 pi, right? That's the time that it took you to travel the entire circle of f dot b, right? Remember this, f dot b. The velocity of the circle, the equation of the circle was cosine of t sine of t, so the velocity is negative sine of t cosine of t dt. And again, remember that on the circle, so this gives you the integral from 0 to 2 pi of minus x sine of t plus y sine of t plus x cosine of t dt. But along the unit circle, x equals cosine and y equals sine, so you get the integral from 0 to 2 pi of minus x cosine of t sine of t plus sine square of t plus cosine square of t dt. Okay, and so this gives you the integral from 0 to 2 pi of 1 minus cosine of t sine of t dt. And well, the first integral is just 2 pi, and the other integral, what's the integral of this? You can make a substitution, like say u equals sine of t, and so it's like minus sine square of t over 2 at t equals 0, t equals 2 pi, and that just gives you 0. So you get 2 pi, which is the same that we found before. But notice that this is how we would have found it originally, and now we have this other method to find the integral. So what I'll show you next time is a nice result where you can use the, so at this point I have been using the Greens theorem to say, oh, if instead of computing this integral, you can compute this double integral. But actually, you can use this Greens theorem in the opposite direction. So you can use Greens theorem to compute a double integral in terms of an integral on a curve, and that's what we will use next time, which will have some nice applications.